Next, we have Jessica Cross. We'll talk about stretching the scales of surface ocean observing systems, biogeochemical observations from the sail drone USV. Yeah.
Good morning, everybody. It's so good to be back with you at OCB. This is one of my favorite meetings that I come to every year. And I've essentially been coming since I started graduate school, so it's a real privilege to have graduated from mic running to being in front of the room. I want to emphasize this week that I work for a program that's called Innovative Technology for Arctic Exploration, or ETE. It's that logo right there. And we have been working with the sail drone for a couple of years, but at this point it's really expanded into a number of projects that are across our lab. So today I'm going to be talking about some work that doesn't 100% belong to me. I know a whole lot about the platform, and I'm really proud to be able to represent the real diversity of work that's going on with this platform at NOAA right now. So the joke that I like to make about designing observational systems is that ideally we'd like to be able to collect enough data that we can make the perfect model, right? That's what we're here for. We want to make the matrix. We want to be able to perfectly predict the weather. We want to be able to perfectly understand ocean circulation. We want to deeply understand our ecosystems so that we can sustainably use them for human development. But as scientists, this is really our obligation, right? Given infinite time and resources, we ought to be studying everything. That is the philosophy that is behind science. And those two things actually mesh, those two ideas actually mesh up really well, because the reality is that we need to understand everything in order to make our perfect model, right? Not only to understand the global system, do we need to understand biogeochemical cycles, but we also need to understand these really fine scale, fine mesoscale patterns in the ocean. We also need to understand what's happening in the atmosphere, because all of these things are connected. We have to be able to understand our observations across these really broad scales in order to make even imperfect models like the ones that we have right now. So the technology that we have to make these kinds of efforts, this is a diagram that you've seen in both of the last talks that has come out. This is slightly modified from that. It's essentially got our space scales along the bottom and our time scales along the left, and shows the different kinds of platforms that we have right now. A lot of us work with fixed platforms, but we also have ROVs and UAVs and satellites, and it's the combination, as Craig was just saying, the combination of these different kinds of technologies and these networked technologies that enable us to get a really clear understanding of what's going on. And right now, we actually do have a pretty good observing system, especially for carbon. This is a diagram of all of the data that has gone into SOCAT over the last couple of years, primarily moorings and underway ship tracks that help us measure CO2 fluxes. And both the moorings and the underway ship tracks are giving us climate quality data. And over the past 15 years, we've been able to reduce our uncertainty in global CO2 flux by about 50%, which I think is a really profound technological achievement. Additionally, the instrumentation is getting sensitive enough, and we're supporting it well enough at this point that we can start resolving this subscale seasonal variability. But this still isn't the matrix. We could still be doing better, right? There are still gaps in our observing system, and we would like to be able to expand those as we can. So I'm going to come back to this diagram and talk a little bit about issues of scaling for a minute. I actually wish that this diagram was in 3 dimensions. I would like to know the frequency of sampling as well as the duration of sampling. So I want 2 time axes, if you will. Depending upon who I'm talking to, I will often modify what that y-axis is supposed to be. Because the reality is that the sail drone, which is what I'm going to finish this talk talking about, is capable of sailing multiple thousands of kilometers, and it can collect this 1-second data. However, it's a really powerful platform that also enables us to collect this 1-second data over extremely long periods of time. So even relative to the boxes that you see on this scaling diagram, the sail drone is really stretching our capacity to be able to make these observations across multiple scales. So before I get into some of the projects that we're working on with NOAA, I wanted to talk a little bit more about the platform and what it is. Essentially, we are using it to build, connect, and explore. Those are the 3 words that we came up with at PMEL. I'll talk a little bit about how we're using it as part of the Ocean Sites program to build process studies around a fixed observing system. I'll also talk a little bit about how we are going to use it as part of the TPOS 2020 program to link the moored sites along the Towelway a little bit closer together. And then I'll talk a little bit about our exploration activities and really the novel ways that we're going to be able to use this platform to collect data from remote and harsh regions in the Arctic. Many of you know me as an Arctic oceanographer, so I'll actually get to my own work at the very end of this talk. So first, a few words about the platform. The real advantage here is that the sail drone is big, fast, and durable. Those are the benchmarks that I like to talk about when I talk about the platform. For those of you who sail, the sail drone is about the size of a Hobie Cat sailboat, so it's about 20 feet long and 20 feet tall. That is enormous, especially compared to some of the other autonomous vehicles that we work with, whether it's the Slocum or the Wave Glider. The Wave Glider is about the size of a surfboard. So what this gives it the opportunity to do is actually move really fast. It's a wind-propelled vehicle, and so that size gives it this enormously large wing, and in the right gale, it can actually make close to 8 knots. So it's a pretty fast platform that allows us to cover a lot of territory. Additionally, it's really big. That large size, in addition to helping us get more wind-driven propulsion across large swaths of territory, it also enables us to put a large variety of sensors on these vehicles. We're not as power limited as we used to be. We have a lot of solar panels on this giant wing. This is actually a very old version. That wing is essentially covered in solar panels now. But we also have a lot of weight. We have about a 200 kilo capacity for sensors, so we can really start talking about putting some of the heavier stuff on, and we can put multiple types of complex heavy sensors on the sail drone at the same time. So we don't just have to focus on collecting physical data or biogeochemical data or acoustic data. We can do all of that from the same platform at the same time autonomously. Additionally, the sail drone is durable. It can be launched and recovered directly from a dock. That's another advantage of its really large size, meaning that we don't need ship time in order to launch it. And that gives us an enormous amount of flexibility in how to conduct our missions every year. So for example, if you wanted to plan a mission to observe a particular feature, but there's an extreme amount of interannual variability in your system, as there is in most of our systems, you would be able to launch this whenever you were able to see that feature and say, oh, there it is, let's go now, rather than trying to plan your mission a year in advance and say, well, we may or may not see it, but we hope we do. I've had missions like that before, so. So additionally, I'll just show some of the preliminary data right here. This is the cruise track from our primary field deployment with the sail drone. It is showing the salinity. So here's Dutch Harbor down south where we launched it. We sailed it all the way up through the Bering Sea into the Yukon River plume. It's the low salinities that you can see up north and back down again. We were actually able to see some really fine scale variable features. You actually have to plot this slightly differently, but you can also see a couple of ice melt pools that we caught out on the outer shelf as well. It was a really successful deployment. We encountered 46 knot winds, which we were convinced was going to knock this thing over and we were going to lose it completely, but instead it just decided to go close to 8 knots. Really booked it. It was a really successful test in terms of endurance. Additionally, one of the things that we were worried about, especially in the Bering Sea, which is a highly productive system, is biofouling. And one of the advantages of the sail drone's speed is that it actually moves too fast for lots of gunk to be able to build up on the sensors and the sensor bays inside the platform. We were also substantially worried about jellyfish. This is my friend Yvette Sidden holding up a jellyfish because she likes doing that sort of thing. She's a biologist. I'm glad she does it so that I don't have to. And we were worried that some of the sensor bays inside the hull of the sail drone would get clogged up with jellyfish, but we talked to Sail Drone Inc., the company that actually manufactures this platform, put a cone around one of the sensor bays. It was made out of aluminum. It was really cheap. You could have made it out of a Coke can, even though we did slightly better than that. And it managed to push all of the jellyfish away, and we had no biofouling issues. So I was very excited about that. The sail drone has many, many sensors on it at this point. I think it's up to 54 options, and I'm certainly not going to list all of them for you today. But essentially, we have an advanced MET package with a really high sensitivity wind sensor on it. We have a really basic physical oceanography package that helps us do temperature, salinity, backscatter CDOM, all of those kinds of interesting things. And then we have a eco-puck, which enables us to get fluorescence and a couple of different other wavelengths. Dissolved oxygen, and then this will actually be the first year of deployments that we have with the CO2 biogeochemistry system. If you're more interested in the platform, I'm actually going to direct you to Saildrone themselves. It's just saildrone.com. You can find them on the internet, or if you'd rather not go directly to the manufacturer, you can look them up in Wired or in Inc. magazine, where they've profiled some of the work that NOAA has been doing with Saildrone most recently. So like I said, this is the first year that we're actually going to have carbon sensors on the Saildrone. It's a modified version of the MAP CO2 system, and initial test results seem to indicate that we're getting about the same level of accuracy on the Saildrone ASV CO2 system as we are in the moored MAP CO2 system, which is really good. Adrienne Sutton has been taking the lead on this work at PMEL. These are photos that are courtesy of her. And this is just an example of the primary field deployment that we did just to test the sensors right off the coast of California. We sailed it through a really high variability PCO2 area to be able to test this across multiple ranges. And here's what the data looked like. So essentially we did a calibration test with a general oceanic system. Across the top you can just see the PCO2 overlaid on top of each other. I believe the ASV CO2, the Saildrone is in blue, and then the GEO system is the black open circles that are on top of that. It looks really close, but ideally you should also plot the residuals in order to see that accuracy, and generally both of the systems were getting within about 2 microatmospheres. So we're really confident that this system is working really well, and we're excited to be able to test it as part of these programs this year. So I'll just go into what those programs look like. Remember, there were 3 that we were going to talk about: building our process studies around our permanent observing system, connecting the sites in our permanent observing system a little bit closer together, and exploring new sites that we may not have seen before. So Megan Cronin has actually sent a proposal into exports to send a Saildrone to the Station P site. One of the other sensor payloads on the Saildrone that we're working on developing is an ADCP. So with an ADCP plus a MAP CO2 system on an autonomous sensor, what we should be able to start doing is resolving the impact of vertical velocities on biogeochemistry, on net primary production, on export fluxes from an autonomous vehicle. So we can get a much bigger spatial footprint at the Station P site than we have been able to get before. So essentially what she wants to do is take the Saildrone, sail it in a big pattern around the Station P site in order to build this big process study. Additionally, we're hoping to send the Saildrone out to the TAO array. So plop it right there in the middle. The TAO array is supported primarily by these moorings and by our long-line hydrography cruises that go across the equatorial Pacific every year. But our moorings are fixed in space. Our ships are essentially fixed in time. They provide us one temporal snapshot, whereas the Saildrone is actually going to be able to go repeatedly back and forth between a couple of different mooring sites to resolve some of this variability that's along the line. Hopefully, the goal is to improve our understanding of how El Nino and the equatorial Pacific processes are impacting CO2 fluxes. This is actually going to be a really big advantage. What I'm showing up here on the map, well, the only thing I want you to get from this is sample density. So on the left, what you can see is the number of CO2 measurements that were made in the 2000s along the equatorial Pacific, and then the more recent number of CO2 measurements. You can see that the density has dropped off a little bit as we have started to prioritize other programs as a scientific community. So there's definitely space for this platform to be able to expand our ability to make these measurements. The last thing that I want to talk about is our exploration initiatives. I like to call these tactical deployments. So essentially what we want to be able to do is respond to new features as quickly as we possibly can. I work in the Arctic, as I said earlier, and so this is just showing the mission that we want to do this year, which we are about to launch in just a couple of weeks. I'm really excited about it. You'll notice that it's not actually a ship track that I've plotted up there. It's just zones of different zones that we would like to be able to access. Our ability to access these zones is going to depend on what the ice is doing. We don't know where we will be able to get to when we get there. Normally in the Arctic, if you want to access this particular spot, you need an icebreaker, and icebreakers are expensive. So how do we get around that a little bit? Or how do we respond to these features like ice melt as soon as they're happening, rather than planning a year in advance and maybe getting there too early or too late every year? And so the sail drone is going to launch in a couple of weeks, get up there just as the ice is melting back. We'll be able to look at upwelling along the Beaufort Sea coast, or eddies off the coast of Barrow Canyon, or primary production that's happening over Hannah Shoal, or river discharge that's coming into some of these bays in the southern Chukchi Sea. And so these tactical deployments where we're really making these decisions in real time about how to maximize the value of our science every year, that's something that, that's a new capability, a new privilege that we have of working with these autonomous systems. So the last part of our tactical deployments is that we're actually able to start looking at ecosystem level changes. We want to be able to connect primary production all the way down to upper trophic levels, right? And so we're working with the National Marine Fisheries Service to track what our marine mammals are eating. So whether it's whales, whether it's seals, whether it's pollock, we want to be able to go to these regions where those animals actually are, see what the production is like. We're not just using the sail drone for these projects, but a number of other things as well. The sail drone, I don't know if I mentioned earlier, has a really solid acoustic package. So we can use active and passive acoustics to listen for both fish and for whales and sea lions and seals, different things like that. So again, it's this network of sensors that actually allows us to do these ecosystem level and process studies. So that's really all that I wanted to profile today. I realized that we covered a lot of ground relatively quickly. As I said, we have a lot going on, and it's been a real privilege to work on this project at NOAA. A couple of things that we're exploring in the future. I would like us to be able to start to estimate export fluxes from the sail drone and actually start measuring ocean acidification variables rather than just CO2 flux. We are just now, I heard this week at OCB, talks, poster presentations from a couple of people in our session, starting to look at using LIDAR to look for different particles. There's a group in the Gulf of Mexico that's actually adapting a LIDAR system for the sail drone right now. They're primarily interested in using it to map coral reef structures, but I'm really excited about the idea that we could be able to use it to map particles. And then as well, someone is also working on, Ed Maggi is working on microfluidic sensors for carbonates. If you've ever heard of lab on a chip, I would love to get just nutrients from that, but if we can start getting carbonate from it too, that would be really exciting and free up even more payload space on the sail drone for us to be able to work with a different suite of sensors. The lab on a chips are hopefully going to be yay big with maybe some dye attached to them, but really exciting. Lastly, this program, ITE, Innovative Technology for Arctic Exploration at NOAA PMEL, is not just working with the sail drone. We're working with a number of other platforms and sensor types as well. I really want us to be able to get to the subsurface. We've heard about these surface gliders and how they have the opportunity to help us resolve this interface. Craig, I think you said that they were ideally designed for that. I want to know how they can start helping us look at the subsurface. So if we have to expand into other platforms to be able to do that, these new types of sensor developments are going to enable us to get as complex a read on the subsurface as we currently are on the surface with things like the sail drone. So with that, I think I have some time for questions. Thanks very much.
I have a question.
Yes.
Have you had any issues with vandalism or theft? And are you worried about that? Because there's some places in the world where it's going to be a problem. That's a very pretty toy you have.
It is certainly a very pretty toy that we have. People have stolen mooring floats before, right? One of my favorite stories is somebody that stole a mooring float, put it in their pool. The GPS transponder was still going. And so the scientist actually went and knocked on the guy's door and was like, I would like to have that back, please. So we have not, with the sail drone so far, we have not had any of those issues. We've been working primarily in the Bering Sea, which are small fishing boats. And you can imagine it's probably pretty hard to tow this thing around Because it's so big, you're definitely not going to be able to lift it up out of the water and put it on your tiny fishing boat when it's essentially half the size of the boat. So far we haven't had any issues with that. Sometimes, just in terms of vandalism or damage, it is wind propelled, even if the sensors are powered by solar panels. So in low winds, you can imagine that's a navigational challenge in high traffic areas. I think that the group in the Gulf of Mexico has run into that a little bit, but so far the Bering Sea is low traffic enough that we don't really have much to run into. I will say that it does have send and receive AIS signals, so other ships should be able to see it. The sail drone can certainly see other ships, but it's dependent on us to move out of the way.